Right. Hello, everyone. Just about to stream some more work on my Casio Loopy emulator. Done a bunch of work since the last video, and I actually haven't done a video in a while, so let's just do a quick recap of what this is and what I've done so far. So first off, I'll just sort of show the current version. So I've cleaned up the output a little bit. You can see that, like, basically this is one of the each cycle, and because the system is a RISC CPU, it's pipelined. So each cycle has a different stage of the pipeline that's being executed: the write back, execute, decode, and fetch. And there's also an exis stage as well. And so certain stages can only happen at the same time, and there's all sorts of other rules. Anyway, so you can see basically that we can very easily see which stages are executed for each cycle and what each stage is actually doing. Like, for example, this is fetching from this address and getting this value. So to basically look at what I've done before, so this was episode 3. This is where I ended off before. Just to show where that was, let's check that out. Okay, and make that, run it again. So you can see that it was a bit more elaborate here. It was showing all the different register state, even for registers that weren't changing. Daru2, love that output. Yeah, I was pretty happy when I cleaned that up. I thought it was a lot nicer. It's like more sleek, so it's like easier to see like all of the different. It's just like it's more compressed. I honestly kind of want to compress it even more because right now there's a lot of stuff I don't want to read, like the decode and fetch. It's interesting to know, but like usually you just kind of want to see the executed steps. So I might clean that up in a little bit. Anyway, so this is where we left off before, and just to take a quick look at the code like that, you can see I basically had a very similar structure. The idea is that anytime you did a step, it would run through the different stages, and then these different stages would have different behaviors, and then most of the work is actually being done in stage execute. That's the sort of primary place where stuff happens. And then we have these kind of confusing names here, but these are basically the different instructions. You could have verbosity levels. Yeah, that's a good idea. I did that in the Game Boy emulator. I probably will do that here as well, depending on like when I get annoyed enough with the output and I'm just like, get rid of this stuff. So anyway, so you can basically see that's this sort of structure here. And then there's this decode step, which basically takes the code and then converts it into an instruction, and then basically builds up that structure. So you can see the structure here. There's, let's see, where is that? It's called inster. Yeah. So an instruction basically has which operation it is, and then the N and M, those are the register numbers, and then D and I are either a displacement, which is used for some instructions, and then I is like an immediate value. So let's go back to head. Oh, no, sorry, master. Yeah. And did I close my window? Yes, I did. Okay. And look at this again. I like this so much nicer. Yeah. So one of the big changes that I did was I sort of streamlined these instructions because I found that a lot of them were basically doing the same thing. Anytime there was a read or a write, it was basically just providing an address and then specifying which register it was reading into or the value that it was writing. So I changed that. I added a little comment here so you could see which instruction it is because the names here were not super obvious. And what else? I implemented a bunch more instructions. So as you can see, like the instructions, like if you've ever looked at other emulators, like a lot of times the instructions are pretty complicated because this is RISC. A lot of the instructions are actually quite simple, and it's sort of meant to be that you combine the instructions together. So you can see like NOP does nothing. Obviously, this is RTS, which is return from subroutine. I don't know why it's called RTS. So yeah, I've implemented a bunch of these. I added some of the stall behavior. So essentially what happens is if there's a write back that happens to use the same register as an execute, the write back actually happens later, but the execute is supposed to be using information from the write back, so it'll stall the execute so that the write back will write the register values that are needed for the execute. So it's a bit confusing, but that's kind of some of the behavior that we need to support if we want to handle the pipelining. I was thinking about it, and honestly, the pipelining is maybe like more trouble than it's worth. But oh yeah, thanks Dario too. Yeah, hope you enjoy. I'll probably just be streaming to myself unless people join up. But that's all right. This is what it's all about. So yeah, see you tomorrow. Yeah, so what else? Yeah, a lot of stuff, other stuff didn't really change. This is one interesting thing. I found that there's an address that's being read that looks like it's probably BIOS. You can kind of see it here, actually. I'll grep through the execution. So you can see that I'm actually executing quite a few instructions from this ROM already. And actually, yeah, I don't want that. I need to figure out how to like turn off or basically make it so that the when I do less with color, it'll keep the color. I think I read how to do it, but I can't remember exactly what it is. So yeah, but anyway, if you look at I think it's it should be 668, I think. Yeah. So basically, it jumps to PC 668, and that's not actually where the ROM is. It's got to be something else, which I'm not exactly sure. So, but it seems to be that it's probably some kind of BIOS routine. So what I did to sort of fake that is I made it so that when you jump into BIOS, it just writes in a RTS, which is the return, and then a NOP. And the reason why it has to write that NOP is because in this CPU, the most branches are called delayed slot branches. And what that means is because of the pipeline, they end up executing the instruction that follows them before the branch actually happens. So you need to put a NOP there because that will get executed. And so that's the next instruction is at 66A. So basically that's where we're at right now. Like I said, we are executing quite a few instructions. And so what I'm going to basically do for a while now is just run this. Anytime that I get an instruction that isn't implemented, like here we have this move instruction, I'm going to implement it and then continue and just see where we get. So that's basically where we're at right now. So yeah, let's see. So this instruction is move, and it's move rm/rn. So I'm just going to put that in. And I've been trying to be like a little bit meticulous about putting these in the right place, just so that they're all in the same order. It's a little bit of my, I don't know, just being what's the word, obsessive, but I also think that it just makes it easier to like find stuff when you want to. So this is the instruction that we want to execute, and I'm just adding this to stage execute right now. And this one should be really simple. If we look at the instructions here, we can see that's this one, data transfer. And it really is just write one register to the other register. Now the only thing that I've been sort of being a little bit careful about is looking at the pipeline behavior, because I did find that one of the instructions that I implemented had slightly different pipeline behavior than I would have guessed. So it's just good to sort of take a look at the docs here and just see what it actually says that the behavior is. So I'm going to try and find it. Let's see if I can find move rn. So that's here. Yeah, that's not it. That's not it. All right. Let's see if we can find it. It's going to be like at the end somewhere. Not this far. Yeah, it's going to be here probably. Register, transfer. It's probably one of these. Yeah, this one. Here we go. So yeah, it looks like it's a straight up, it's a normal instruction. So you can tell because it's just got IFID-EX. There's no memory access. There's no write back. There's nothing else. So that means that we can actually just do this like we would for, come on, like this. We basically write to Rn and we read the value of Rm, and we'll execute that. And yeah, so I kind of lost track of that, but we can see execute. I think it's this one here. So I really need to get the less working. That'll be good, because like this is this is not working properly. So actually I'm gonna take a quick look to see if I can figure out how to do that. Let's see. Less color. Okay, colors and less. It looks like I already searched for this. Less filter. Less -R, is that it? Raw. Yeah, that looks right. So if I do awesome. Okay, cool. Not too much of a digression. Okay, so yeah, let's find that move. That was move R4 R12, so that's here, and then we do the execute. Oh, actually, I was normally writing out the values after that, so let's do that. So I have this convenient function print registers, and it's a vargs instruction, or function, I mean, so that you can actually just pass multiple registers and write them all out, which is actually, it's pretty cool. I don't use these enough. They're pretty nice. So let's just rebuild that. And yeah, so we get our R12. That's this value here. And our R4 we probably will see somewhere else above. Yeah, here it is. So yeah, that looks good. And then we do another move. And so now it looks like we're bailing on add -1. So that one should be pretty straightforward too. That should be add immediate Rn. So that's this one here. That's up near the top. So let's add that one in. That'll be add. I think it's just add immediate Rn. Let's add immediate Rn. Again, I'm guessing this instruction is going to be really straightforward. Yeah, so let's see. Yep. Again, just same as the other one. And then if we look at the behavior of it, be nice if I could actually have both of these locations open at the same time, but that's okay. I'll just scroll through. So here's add immediate, and it looks like the behavior is that it does a sign extend on the immediate value and then adds it in. So I've already done the sign extend. You can see that here format ni does that. Yeah, already does the sign extend. So I don't actually have to do anything like that. I can just directly modify the value. So we'll do, oh, actually I have a regs for this. Yeah. Regs plus inster I, which is the immediate value. I'm pretty sure that's it. And actually, let me just see if I forgot any of the other eState regs in here, because it's nicer to just be consistent. Looks like I didn't, so that's good. Okay, I think that's right. So yeah, let's add in our print registers. And here we're going to print rn afterwards. And we'll do sr again. And there's our add, which gets executed here. It's adding -1 to 10. And our R10 was, well, we just moved it here. So yeah, that looks good. Okay. So now we need test. Let's take a quick look at test, what that does. Here it is. So test, okay, this is interesting. So this sets the T register, which I haven't used yet. I think I have a register for this. I think it's called, I think it's SR. Is that right? I should check. Let's see. SR register. Oh, actually, I found it at the top. SR. No. These tiny little scroll bars. So annoying. Okay. So yeah. Yeah. So oh great. SR has a bunch of stuff, but it also has the T bit. So let's see. How did I do that? I have SR here. There's register SR. And it looks like yeah, so it looks like I'm not special casing that. That's fine. I think it's probably better this way. Sometimes it's nice to have these like separated out into their separate flags. But I think because of the structure of the CPU, it's probably better to keep it as a real register and not have to like synthesize it based on the state of the flags, because I don't think we're actually going to be testing these flags a lot and setting them. With the Game Boy emulator, I found that it was actually very convenient to have it so that the flags were actually a separate value, like a separate U8 value. And the reason for that was just that then you don't have to do all these like shifts and adds and masks and things to be able to set them. You can just write them directly like you'd write any other value. I didn't actually test to see if that was faster, so it might actually be that I'm wrong about that, but it certainly made the code cleaner, that I didn't have to do like bit manipulation to set flags, and you do them all the time. With this, you're really not setting flags all the time. In fact, there really aren't flags like there are in a normal or like an old school CPU. So so yeah, I feel okay just doing the mask here. In any case, we need to implement this instruction, so let's go to our stage execute and add that one. So this would be test rm I believe. Sorry, it's tst. That's the instruction there. Let's just grab that. And yeah, so we're going to want to basically do what it says here, which is and them and check for it to be 0. And if it is 0, then set T, otherwise clear T. So that's pretty straightforward. We can just do essentially register SR. Let's see, how do I want to do this? I guess I want to mask it off and then set it. And set it conditionally. Yeah, I can do that. It'll be fun like this. So then do if inster m and inster inster n. And yeah, actually this needs to be not equal to 0. So actually I can just do that. Sorry, it's equals to 0, so it should be that. Yeah, that seems right. Yeah, well, it's a bit cheesy to sort of like not actually specify the T register here. I don't know. I'm thinking, yeah, let's do this. Actually, let's write out M, N, and SR. Yeah. Is that what I want to do? I mean, I think this will work. Yeah, let's take a look at it anyway. Yeah, so there's the test. Comparing 3 to 3 and sets SR. Oh, so obviously you're comparing it to itself, so it always will clear off the bit, which it does. So it's a bit weird. Why would you compare against yourself? Huh. Oh, that's checking for 0. Right. Yeah. Okay. So, yeah. Like I said, I think it's a bit cheesy to sort of implicitly have that as to set the 1 bit for T. So I'm actually going to create an enum for that. Let's see where to put it. I guess here's one. And we'll call this SR bits and call it SR T 1. What were the other bits? Yeah, it's not that one. So we have M and Q, I3 through, okay, those are interrupt mask and the S bit. So yeah, so this is actually bit 0. This is bit 1. That's bit 4. Oops. Then Q is 8. And M is 9. Okay. And then I'm going to want to, so I'm going to clear off T. Actually, I guess I probably want these to be masks. That's probably going to be more useful in general. We'll do that. We can do that, and then I guess this is clearest. So let's see, if they're non-zero, then you set the bit, and if they're, or sorry, if and equals 0, let's do that again. you set it if they're equal to the if they anding them equals 0. So this should actually be this. Yeah, so that gives us the same result, which is that's 0. I'm kind of wondering if it might be nice to, rather than writing out SR, to write out T here. I wonder. I won't do it for now. Yeah, because mostly it'll be kind of annoying to do, but it's probably worth doing at some point. Okay, so moving on to the next one. Looks like we're failing on BF. So that's a branch instruction. BF. Let's see, probably this one. BRAF, BF. There we go. So this one. This is a branch without a delay slot. So it does not. It basically introduces a bubble. This is actually different than any of the other branches I've implemented so far, but I think it should be pretty straightforward based on the fact that we already have the pipeline set up for this sort of thing. So when t equals 0, then diff times 2 plus PC, otherwise NOP. Okay, should be pretty straightforward, so let's take a look at that. So we've got BRA, there's our BF. So BF looks like BF plus a label. Haven't been putting the labels in the names here, so it's fine, I guess. Okay, so basically we say if regs register SR and SRT, then PC equals I think that's probably right. Let's see, this is format D, so it's actually D. It's stored as the same value, but it's nice to be consistent there. Otherwise it's a NOP, which we'll get implicitly, and we'll print out PC, because that's the one that we care about. I guess we could print out SR as well. It doesn't hurt. So yeah, we'll print out SR and PC. And so yeah, then the difference is normally we do a stall after the branch, but in this case we're not. Wait a sec. Hold on. Actually, might need to do something special for that now I think of it. So if we look at the branch instructions, yeah. Right, so when the condition is satisfied, you do an execute, and then it discards the decode and then does the fetch of the third instruction. When it's not satisfied, meaning the branch isn't taken, it actually just goes normally. And so that differs from, does that differ? Oh, I see, okay. So the difference with the delay slot is that the delay slot means that that next instruction actually does happen. It gets decoded. Yeah. So it's basically the same. Let's see if I can find, yeah. Yeah, so this is the one that I've already implemented, like branch here. Basically, it does not do the fetch here. Interesting. I wonder if that's how I do it now. I probably don't. So let's find. Let's find a branch. So this executes a branch, and oh yeah, so then I stall and then do decode fetch. So that's right. Yeah. So the difference with BF is that it actually is supposed to fetch, but then discard. So it's not a stall. It actually basically deactivates the decode pipeline when the condition is satisfied. Sorry, this is the one I'm looking at. But yeah, basically it's the same idea. Yeah, okay, well, let's see if we can get that right. So I think that's actually a special thing. So we basically have all the pipelines here now, or all the stages. This is instruction decode. And what we want to do is, if it's taken, we set this to being not active. Yeah, but it doesn't stall. So let's see if that does more or less what I expected. So this is saying it wants to branch to 782, but because T is not set, it doesn't branch, and it basically just keeps running. So it does the decode and does the fetch, and then it runs the move from the next location, which is 7xc or 7c6. Yeah, so it's just fetching from the next location. That looks right to me. It'd be nice if I had an example where it did take the branch. I guess I can just hack that. Actually, I want to check that again to make sure that I wrote that properly. No, not test. I want BF. When T equals 0, it branches. So this should actually be that. Yeah. So now we're actually seeing it should take the branch. So it sets the PC, and it does do this fetch, but it's thrown away. Or it should be anyway. Oh, look at that. Actually, it decodes. Interesting. Yeah, that's wrong. It's wrong, but actually, maybe I don't care. Now that I think about it, because like, it doesn't hurt anything to do it, to decode this, because it won't actually execute. Oh, actually, will it? Yeah, actually, it is about to execute. Yeah. Wait. Oh, this is fetching from the new location. It should actually be fetching from the old location. Huh, that's interesting. How does that work? Oops, where did that go? Yeah. Right, so it's supposed to fetch the old one and discard it, and then fetch from the branch destination and then continue normally. So yeah, to get this to work properly is a bit annoying, because it means that the execute step can't actually update the PC, because the fetch will use the current PC, and it's not supposed to. It's supposed to use the old PC. So I don't know. How much do I care about fetching from the old location? Like, I could just put this in as a stall and it would be a bug, that it doesn't actually fetch from the old location, which probably doesn't matter because the information is being thrown away. So I think I'm going to do that for now because it's simpler, and just put in a to-do. Because realistically, the fact that the fetch, it's possible that fetch actually could have behavior associated with it, but it's pretty unlikely that it will. Yeah, it's pretty unlikely. So to do that instead, we could do this and just put in a to-do. This is actually supposed to disable the code stage and fetch from the old PC in this cycle, then throw the fetch away. Behavior here is likely not to matter since it's not often that fetch I don't know. It's a silly comment, but it should be fine. Alright, so let's see what that looks like. So now we have BF here, doesn't execute. What is it decoding? Oh yeah. It needs to disable that decode still. Yeah. Okay. Right. So now it's just doing that fetch from the new location in the next cycle, and then it does the decode of that. Yeah, of the branch location. Yeah, that seems right. Cool. Okay, so then the next instruction we need to implement looks like move B, and then according to my sort of weird naming syntax, that would be ARMP RN. So the A means address of, like that's the @ symbol, and the P means plus. And you can sort of see the name here. There's @ plus there. Okay, so that's the one we want. And we'll implement that. That should be below EMRN, which we have here. And that should be move B plus RN. Okay, so this should be very much like this one, only it's a U8, and that's it. I haven't actually implemented this yet, so we'll do that. We read U8. I haven't implemented that either. That'll be read U8, so we'll go find that. I might as well do write U8 as well. Okay. And yeah, why not? I'll add it here too. Actually, it should be a copy of this one. Let's do 16.8. Oh, actually, yeah, I want that one too. For some reason, it wants to flatten that one out. All right, let's see if it does the other ones. No? Does that mean that I copied something weird? Oh, it's probably just short enough to fit on one line. All right, well, cling format, whatever. Okay, so that's that. But it needs to be implemented down here as well. So what we do is add, and again, this can just be switch those. Should sign extend? Probably. I wonder, actually. So let's see. Let's look for move B. There we go. So move B, that's this one here, yeah. So there is a sign extension. And yeah, let's see, what do we have here? Move B. That's this one here. Yeah. Okay. So we sign extend and then write the value. That all looks pretty good. Let's see. That might just work. Oh, it's not handled in the switch. Okay. I'll add that in even though we haven't seen it yet. And I haven't actually been implementing any of these write functions, mostly because I don't really know what they're supposed to do yet. I'm hoping what'll happen is that when I start to be able to look at the writes, I can sort of make a guess as to what they're writing and why. But yeah, that'll be interesting. There'll be some tricky debugging, I'm sure, that'll go on there. So okay, so there's our move B. It wants to write to R12 the value of R11. I should write out. Where did that one go? Yeah, I should write out RN. Okay, there's our move B here. So it's writing 0, so not very interesting, to there. And that looks like it worked right. Okay, so now we're doing xtu.b. That's probably a sign extending xtu.b. Not the most exciting thing in the world, but these are the things you have to go through to get your CPU working, emulated CPU. Okay, XTUB, yeah, 0 extend. Oh right, yeah, XTU. Okay. So basically just zeroes out the top bits. So that should be pretty easy. Let's just see what the, yeah, so there's XTUB, and this is just another one of these instructions that very simple to implement. Almost kinda makes me want to implement a bunch of them, but I'm gonna stick with my current pattern of just only implementing when I actually see them, just because then I can actually verify that it worked properly. So this should be, sorry, it's extending what to what? Right, always, n is always the destination. I should know that. So basically it would be like that, I think. And then we'll want to print. Do we need to print both? Yeah, why not? Oh, that's oops. Yeah. And we'll take a look at that. There's our X2B. Of course, it's sign extending 0, so we see nothing useful here. But you know, it didn't do the wrong thing, so that's good. Then we have our add 2 here. That looks right. Then we have an extend UW, so it looks like we're going to get a chance to write that one. Should be pretty easy. Let's just make sure we have this in the right place. Yeah. Oops, whoa. And this should just be that, I think. There it is. And again, I can't actually tell if it's working, but you know, probably works. Okay, and then what do we have after that? And. Okay, so I'll look that one, and RM, RN. That should be here. Okay, yeah. So I already looked at this one and saw that it was basic arithmetic instructions, so there's not going to be anything funny happening with the pipeline. And almost certainly this is not doing anything, yeah, weird. It looks like it's just a straight up and. Okay, so we should be able to just do that. And let's just print out M and N. That should be all we need there. Okay, so we're ANDing it with 12, but of course it's 0, so it doesn't matter. So now SHL-L2. Yeah. So let's take a look at what that is. SHL-L2. I think this is one of the shifts where it's shifting a specific number of bits. So yeah, so it's just shifting 2 bits. Logically shift by 2 bits stores the result in Rn. So it's just one register. Bits that are shifted out of the operand are not stored. Yep, okay. Sounds easy enough. So we have SHL-L2. We'll put that after RTS. Yeah, it looks right. Yep. So this should be SHL-L2, Rn, SHL rm. And this is another pretty easy one, I think. It should just be that, right? Oops. And then we'll write out that instruction. Did I? Oh, it should be L2. Okay, so again, it's shifting 0, so we're not actually seeing if it's working or not. But it's pretty hard to imagine that I screwed that up, so yeah, I'm just going to say that that's probably okay. Oops. Let's take a look at what I've done so far. That's pretty good. Okay, so now it's getting stuck at add, looks like add rm/rn. Yep, okay. So add rm/rn. And we have add ir, this one. So add this one in. Add rm/rn. Another one of these easy ones. I like these easy instructions. So it's just going to be that, I'm pretty sure. And then print out those two. Let's see if we can. Whoops. Yeah. So, yeah, adding 0 to 0, so pretty useless. Oh, it looks like we got to the end of how many instructions I was printing out. So yeah, it's it's doing a lot of shifting, which means to me that it's probably expecting to read values and not getting anything interesting. I'm wondering where that happens. So let's see where that first one happens. So it's shifting R2 here. Yeah, where does it actually get that from though? So that's R2, that's R2. Oh, it's moving from R4, extending from R11, then it's extending from R11, reading from R12. So it's reading from here. That's actually in ROM. You can tell because it's OE. So I guess that's supposed to be 0. It's weird that it's doing, I mean, maybe it's probably just doing a bunch of stuff over the entire ROM, because it looks like then it branches. What I really need is to say the PC of the executed instruction, because this is pretty confusing. So I'm actually going to do that. Stage execute. Do I know the PC of the executing instruction? I don't think I have it stored. But I'm definitely going to want it, so let's do that. Oops. So we have stage EX, and it has the inster, but the inster doesn't have the PC. So I'm just going to stash the PC in here because it is really useful. In fact, I wonder if all the stages should have the PC for debugging. Probably should. Yeah, let's do that. Oh, and actually, should it be address? No, I guess it should. No, I don't think so. It's weird that I have this address type because it's like address is obviously U32. Why make it different? But I don't know. Put the PC there and there too. And then we'll just sort of forward it through. Yeah, so basically when you set the new stage active, it should forward the PC through. So you can do that. So what we can do is id equals stage id, code equals code, active, just putting active first, active equals true, code equals code, and then PC equals PC. That looks okay. Oh, and actually, this one doesn't make sense because it's adder. And actually, that's what it should be called. It shouldn't be called PC, it should be called adder, or address, because it's not really the PC. Oh, except for this one already has an address. Okay, it should be inster adder. So that's yeah, I don't know how much I like this, but just adder. Yeah, okay, why not? And then this will break something. Why didn't it break anything? The stage IF not actually use? Oh, it just uses PC. So this is actually useless for stage IF. And actually active is useless too, but I don't know. I guess that's technically a way to do a stall, is to set the stage not active, but I haven't really been doing it that way, so yeah, okay. So let's see. I'll pass through iadder from here, and I'll pass through iadder from PC, and then these ones need to pass through iadder as well, which means that they have to pass it down. Or instead, it's maybe nicer, is that we just sort of forward it through, yeah, afterwards. So just say ma iadder equals ex iadder. We only have to do that when the memory access stage actually is active, but it doesn't hurt to do it. And I really doubt that that's actually going to be like any source of performance hit, so who cares? Okay, so then we have the write back stage, and again, this one does a bunch of this sort of thing. I almost want to factor that out. Yeah, let's do. Yeah, let's see how to do that. I think what I want is to do like this, and move this here, and then move that there, and do that. And these don't need those. Like that. And then instead of a break, we do go to read. And then we do a break. And then we can just do iadder equals ma iadder. Like that. Yeah, I like that. Okay. Let's see, does that compile? Yeah, let's take a look at the output. Oh yeah, so the whole point of this was so that I could have IADR propagating through, which I now do. So I can just maybe put it in print stage. I wonder. Yeah, so actually, let's do it this way, which is kind of cute. We can do, we have active, and we have adder, and then we just say stage. And one of the kind of funky things about C is that you can basically cast these to a stage, and because it has the same structure, it's like legal to do. So this is kind of the way you would do like inheritance in C in a way. So this does mean that the it does mean that the names are going to change, so a bunch of this will break. That's okay, we can just conflicting types for stage, so I probably already have, yeah. So these aren't actually used anywhere, I believe. Yeah, and that's the new one I defined. So I'm going to get rid of this because these enums aren't used. Right, so now all the actives have to go through this stage. Oops. Oh, I don't like that very much. I guess you could do I mean, this will work, but it's pretty verbose. I think that'll work, yeah. So but honestly, if I can just make this like base or something, it's still not short enough. Yeah, if I just called it like S. Short names are bad, but I don't know. I kind of don't care that much about that. So yeah, let's just call this S. And then we get this, which is, yeah, it's a little nicer. Okay. So now this is S. This is, oops, S. I might change my mind and decide that I hate this, but for now it's okay. And then this is .s equals that. All right. Oh, and actually, oh, this is cute. Actually, I can make this nicer because I'm setting this to false, but I could do it later. And if I did it later, because I already know that this is active, then I can just pass it straight through like that. That's really cool. So I just have to make sure that happens afterwards, like that. Yeah, that's cute. Okay. And same thing here. Honestly, I'm just gonna pass the IADR here. And look, I didn't even use address. And we can do iAdder equals iAdder and active true. No, stop. And of course this is going to affect all of these. That's okay. That's wrong. It's funny because a lot of these are so similar. I might want to, I don't know, come up with some nicer way of writing that, but whatever. Oh yeah, and then I need to copy these for those. Okay. Right, and so now this needs to pass through the iAdder. We can remove it there. Yeah, do I want to just remove it? I don't know. Well, let's just see what it looks like. So this should be like that. Seems pretty weird to do that. Could pass down E instead. That's maybe a bit nicer. It's a bit weird though. I don't know. It all seems pretty silly. Yeah, let's pass E instead. I don't know. I think I like that better. And then this can just be E state pipeline EX S iAdder. No, S. That's pretty weird. Let's just see. Yeah, I think that's right. Because, you know, honestly, there's probably other stuff that I'm going to want the emulator for. Maybe not, I don't know. But this is just a helper anyway, so. Okay. Why doesn't it like that outright? Can just pass E here, which is a bit cleaner. should be all of them. This is that. That's that. Yeah, and so then this one we can do the same thing and just pass through .s equals this is mas. Oh yeah, and that goes away. Okay, that's that. Oh, and actually, yeah. Not sure if that was worth all this hacking, but we'll see. Oh, broke something. What did I break? Okay, fun. Oh, I did this thing. I set active to false and then I propagated it through. Where did I do that? Yeah, here. So this has to be the same way. Do it afterwards. I think. Probably best to do it at the end all the time. It's just a little bit clearer. It's sort of like saying, okay, I just finished this stage. And I don't think there's any case where we sort of like change that inside the actual stage. I don't think. Yeah, that's better. Okay, so all of that was so that now we have the information necessary to print the stage. So print stage can take a stage pointer. Honestly, it can just take a stage. And then when it writes out the name, how we want it to look. Yeah, we can just do like that. Do no, that's the adder, like that. And so now this will have to I'm sorry, this is fetch. Yeah, so it won't actually let me do that. That's funny. I guess what I have to do is say that. Yeah. It's a bit weird. I thought you could actually cast them, but maybe I'm wrong. Well, anyway, doesn't matter really. And this will be EX. And this will be MA. And this will be right back. Okay. Okay, so now, yeah, that looks pretty good. Oh, but fetches are wrong. So this should, yeah, this should set IF S IAdder equals PC. see. Yeah, looks right. That's pretty cool. Yeah, so now you can really easily see. I kind of want to change the color of that. I don't really like it being that color, so I'm going to change it to this, I think. Yeah, that's all right. Yeah, okay. Well, anyway, back to the whole point of this is that now can actually see what was actually being executed. So we can see if there's like a loop or something. So in this case, we do 782, and yeah, so now we can easily see that this is a loop right here. And so it's incrementing R12, then it does a whole bunch of stuff, and then it loops around again. And so then it increments R12 again, and does a bunch of stuff, and loops around again. This time, yeah, it's still read it's still read 0. So this might execute for a while. What is it looking for? It's looking for R3 to be 0. Yeah, so there's F2E, and there's F2B, F2F, or 5.2, I mean 5.2D. Yeah, so it's counting down. So this is going to loop for a while. So probably the next thing to do is to do like Darutu was saying, and actually add some kind of verbosity mode. But before I do that, I'm gonna probably do a commit, because there's a bunch of changes here. So let's see what we got here. So this is like implement instructions, and we'll take a look at which ones we have. We have add RN, we have add immediate RN, and RN, BF, oops, we have this one. Oh, stop. This one. This one. Don't really need to document all this, but I'm kind of enjoying it. It's fun. And then the other sort of important thing is also add stage base struct included by in all other stages. This stores whether the stage is active, as well as the instruction address executed. I think that's pretty much all we have here. Yep, okay. great. So now we'll look at the output without any of this, and yeah, it's pretty verbose. So what I'm thinking is I'm going to want to be able to disable, like only write out the execute. One thing that's a bit annoying is because I've separated out write back into its own stage, any instruction that does write back, you don't know the value that it's going to write until the access happens. And so if you only write out the execute stages, you won't see the what actually got loaded. I'm going to say that that's not a huge problem for now, but you may want to improve the output for that. So let's just do I want to do some kind of like cheesy verbosity. It's kind of how I've done everything else so far. So okay. So if things are verbose, then we basically print out all the stuff. So in fact, actually, it might be nice to have multiple levels of verbosity. So like this could be 1, 2, 0, 1, 2, and then we can check for it. So what we can do is if verbosity is greater than, I'm almost certainly not going to want this to be compile time. Yeah. But for now I will. So I'll say if it's greater than 1, because normally I don't really care about fetches. Then we print that. And then if, same with this one, kind of don't care about those, about decodes. Executes we usually care about, but I think we'll only care about those if it's greater than 0. This does mean that we want something special for these print registers. So I think the way to do that is just to be sort of cheesy and do something like print registers and we'll just say if verbosity is greater than 0, then this is print registers VA args. Otherwise it's nothing. I can just do 0 there. And then all of these, let's see, what's the magic? Let's word. There we go. Oops. Okay. And then this prints the new line, which would be from the stage. So I'll say 0. Yeah, this is pretty hacky. I'm gonna want to do something nicer than this, but it's okay for now. Let's see. And then the access stage, I think it's the same thing. I want this greater than 1. And then all these printfs. Yeah. It might be that what you want is like a printf function, but I don't know if I want to really go down that route because I'm not going to have it be compile time for long. So for now, we'll basically just do it like this. That's what I did here, right? Yeah. I don't care about that too much because it's like only a few places. And then this one's the same deal. Right back, I only care about if the verbosity is high. And then also the stage, I only care about if the verbosity is high. Or printing out the step, I mean. All right, let's see what we get there. All right, so now, that's pretty cool. Now we just get execute, which is basically what we had before. And then if we bump verbosity, then we get everything. And then if we kill verbosity, then we only get these, which is, must be something that I missed. Probably this one, yeah, reading. I'm gonna, yeah, I'm gonna say, I don't know, this is fine for now. Yeah, so now we get nothing. Normally what we want is this. Yeah, that looks pretty great. I really wish this was aligned, but I'm not gonna get too obsessive about these things, even though it seems like I have with pretty much everything else. Okay, so yeah, let's just make that basic verbosity define. Now we can crank up the number of instructions we're executing. Let's just see what we get. All right. So it ran them all. Looks like we're still in this loop. Yeah, it's only at 412. So might have to start doing stuff where we work on a debugger, like a real debugger, because like in this giant loop, it's, I don't know. Anyway, for now we can crank it up, and it's going to spew out tons of data, but that's fine. Not super fast. Okay, looks like it finished. Yeah, so even right now, I know I'm gonna want something better than, because I want to basically be able to turn verbosity on and then disable it in this loop and stuff, and I'm going to want to be able to set it from the debugger and so on. So yeah, I need to do something more clever. So let's do something more clever. Verbose. It's actually not that hard, really. All right, so we have our emulator and we have our state. So we can just do verbosity. Kill this, and then basically everywhere we were doing this, we just change it to a normal if. Oh, sorry, did I say greater than 2? That's weird. weird typo. It should be greater than 0. And then print registers. Yeah, basically this just needs to only print registers if so I want same thing I did before. And then print registers will look at the verbosity, and since we only use it, I think we only use it in this, yeah, we only use it here, so we can just basically say if e verbosity is greater than 0, then, or sorry, if it's equal to 0, return. So we can actually just do it here. Okay, and that looks fine. Let's take a look at that. So we need to get rid of more of these. So that's the same as this. But actually, well, it's fine for now. Should be 1. Yeah. Yeah, see, now I'm kind of wishing I do have a verbose F. Still not going to do it, though. Okay. And now, that should be initialized to 0. But we're going to want to initialize it to 1. Oh, it's not in state. Yeah, okay. Let's just kill that previous commit. Pretend it never happened. Okay. So now the cool thing is that I should be able to change that. So I could do something like this. And then say verbosity equals 2. We should be able to see the difference. So you can see it's verbosity 1, and then it switches to verbosity 2, and that looks good. I feel like the next thing that I want to work on is adding debugger features, but that's a bit more work. I don't really have a whole lot of time. Well, well, let's just get started on it. Cause yeah, I mean, even as it is right now, it's like I said before, I'm not gonna want to sit here like and watch this. It takes too long when it's printing everything out. Like, what was that, like a couple seconds before we can get to the next instruction. I guess, yeah, I don't know. It might be, maybe I should just continue on the current track of printing out instructions, or working on execution. So then what I can do is basically set verbosity to, oops, set it to 0. Let's see how fast that is. Alright, well, good, but I didn't actually test this out. Huh. That's weird. Shouldn't be printing that. Why is it printing that? Am I setting it somewhere? Yeah, that's bizarre. Where is this getting set? Is there any just not save the file? Yeah, okay. Gotta save the file, people. All right, so yeah, okay, so I actually can just continue to work on these instructions, but the problem is I won't be able to see the output of the instructions. So I kind of have to, like, what I want to do is almost like rewind and execute it again or something. If it fails, I'm not sure exactly what I want to do there. Yeah, because I've got, like, where is it? Stage result unimplemented. Yeah. Okay, so what I can do is, currently I'm not actually saving that. Yeah, I just throw it away. So what I can do is say stage result equals stage execute e result. And then if the result is unimplemented, then return that. How about that? Okay, and so then I can do this. Say if result equals unimplemented, then do it again? I don't know. Will that work? Boo. Oh yeah. Oh, and there is no result. This should just be stage result stall, and shows that. And this should be stage result okay, like that. have a result, so we'll call this SR. We're being cheeky. Yeah. That did not work. Wait, so if I, because it should print out twice. Is it because I do unreachable here? Yeah, it doesn't exit. So I don't want to do that. We'll do this instead. Well, what we'll do is we'll make it so that this is just print error instead, and return result. And then, yeah, so now it's going to keep executing it a bunch. And we can just exit out there. Yeah, so now we can see it twice. And then we can change verbosity to 2. We can see exactly what that stage looked like. Which, yeah, that's not bad. Yeah, I like that. Okay. So let's see. Yeah, we'll probably do want to do something more clever later, but this is fine for now. Repeat. Last stage if the yeah. Okay, so now, rather than doing the debugger stuff, which is a bit more work, although I do want to work on that next time, I think I'll just implement a few more of these and then probably call it a night. So, what do we have? LDSL. So this is LDSL PR. So PR is the return register, the what do you call that? Like basically it's the register that gets written to when you do a branch. So you want LDCL. I think I've already implemented one of the LDCs. Yeah. So this would be LDSL PR. It should be LDSL PR. And yeah. So R15 must be like used as the stack pointer. And this looks like it's just popping the return register from the stack, which is a pretty normal thing to do. So what we're going to want to do is basically very much like this, which except for it's going to read into PR, and I think it doesn't stall. Could be wrong, but I'm pretty sure this doesn't stall, unlike LDC. So we'll see if we can find it in here. Yeah, so it's the same as an ordinary load. Yeah, so it means it does not stall. Oh, and now we're executing 6644. Interesting. So that might mean that the BIOS is larger than I thought it was. I actually, I want to see what we were executing before, 634. Yeah. So what I'm going to do is, yeah, I'll just do if E state pipeline ex iadder equals 634. Is that it? Yeah. And I'm gonna up the verbosity. Oh, this would be. It's a long name. And it did not work. Why did that not work? Should be that. There we go. Cool. Okay, so this is the kind of thing that we want our debugger to be able to do. Yeah. So what's happening here? So we jump to R3, which we get from where? Also, this JSR really should show you what R3 was. Well, I guess we know because it's PC. It's going to always be the same as PC. But yeah. It's weird that they do JSR at, because it's actually not reading that from memory, but whatever. Yeah, but so we don't see R3 here, which is annoying. It must have gotten loaded earlier. Okay, well, what to do? What to do? I mean, I could just go backwards in instructions, but that's not guaranteed to work. Let's see. Oh yeah, see, and now I'm in this loop. So, yeah. Let's try to. Oh, that's weird. Oh no, I see. Yeah, so this this is another one of these tricky delay slot things. So it does a branch here, but it doesn't branch immediately. It does the delay slot, and then it branches. And the delay slot loads the PR back. I wonder how that's supposed to work. Oh, but it's not doing JSR, yeah, or RTS, which is the return that uses PR. So, but yeah, we still don't know where R3 was getting set. I mean, it looks like it was. It looks like it was here. Yeah. Okay. Well, so basically, just bite the bullet and set it here. And we'll just see everything. There'll be a lot, but not that much. Okay, so yeah, there's our R3. Maybe I'm just missing it. Oh yeah, here it is. Yeah, there's the R3. Yeah, so this is the case where it's a bit annoying actually, because we read into R3, but because I wasn't actually displaying the read. So yeah, I'm sure people who are watching this or will be watching this on video will be like, "It's right there, you idiot." Yep, there it was right there. So anyway, so this is almost certainly BIOS. So yeah, and you can also kind of see, like, the other place where we're branching to BIOS, what was happening is it branches to a certain location, but it also sets a register to a particular value, and that must just be saying, like, do this operation. Like if I find one of the other JSRs, like this one, 668, you can see it does a JSR, and then it also does a move it moves this immediate 2, whatever that is. So that's the next JSR we do. So I'm just going to go up to our BIOS and say, yep, BIOS is bigger than that. Yep, BIOS is bigger. Increase the size, and you know, honestly, I don't even care that this is, I mean, what is this, 64K? And so then the address that we're looking at is 6644, and we'll do the same thing. Just make it do nothing. Do I like that? I don't know. Like this is fine. Okay, so let's try and find that. So there's our 6644, and then we just branch back, and then the next one is we jump to, uh-oh, invalid. Oh, 5, okay, so this is another one. So R12, which we loaded. All right, this one is here. No. What? Yeah, we load it here. Okay, right. So yeah, we load R12 and R3 sort of around the same time. This one looks a little bit different, but I'm going to go ahead and say this is also just some BIOS routine. So 5F4C. Oh, and this is real bad. We're now at FF. So how did that happen? Oh, yeah, we're reading values. We're reading bogus values. So maybe I need to have like real memory backing some of these. Yeah, I probably do. Because what's happened here is we loaded PR from this address here, and then basically what I'm doing now is if you load an illegal value, it just returns all Fs, which we then branch to. So it was actually trying to store its return address, and look, it's doing the wrong thing here too. So it's doing all sorts of wrong things. In fact, it might mean that these addresses are wrong. I'm gonna take a quick look. So you can see some FFs here. But that looks right because we're subtracting 1 from R10. That one also looks right. This is the one that's wrong, where we're reading from R15 and we get bogus values. So let's take a look at those 090 addresses. This is writing to that address. So it looks like we write up to, or at least we're reading up to 7FFFC. This has got to be the stack. Yeah. So let's just grab that. And where's our address map? I'm going to call this RAM because why not? And we don't really know where it goes to, but I'm going to guess that it's like that. Right? And what does that give us? 7FFF. That's 8 times, oops, 64K, 500K. That seems reasonable. Yeah, okay. So, yeah. So let's add that in. Into our state. So our state is going to be pretty big. That's okay. Are we allocating this on the stack currently? I think we are. So we're probably not going to want to do that. So I'll do where to put this stuff. Here's fine. Random size. So we'll call that 512K. Oops. Yeah. Okay. And then, like I said, we're going to want to allocate that now. So we'll just do this. Alternatively, you could just allocate the memory. Which is probably nicer. The reason I didn't want to do that is that I was sort of going with this idea that I had from the Game Boy emulator, where it was kind of nice to have the state as one just big block, because then you can just mem copy for a save state. So yeah, I'll keep it like that for now. We'll see if we have to revisit that. So it still works, as it should. I guess we want to free it at the end. It's kind of silly to free at the end, but it's fine. So now we can actually implement these write functions. Actually, I guess the first thing we should do is map the address. So now we're basically saying plus RAM size. And actually, I should do BIOS size, because we're guessing that this is 64K. Yeah. That's fine. What is going on? There we go. No. Yeah. So what I actually probably want to do, because this seems to be pretty common now, is do base is address and I keep thinking that that's, yeah. And so now I can say this is base, this is base, and that's base, this is base, and then, and even this is base. Even though it doesn't really matter. I'll leave that one out. But what it means is I can actually flip this test and move it down. So how do I want to do that? Yeah, I can do this. And then this can just break out. And we'll do this at the bottom. Oh, but we have to set the type. Where's the type called? Memory map type. Type equals memory map BIOS. And this is RAM. Okay. Just make it a little bit nicer to look at. Okay. And then it'll break out, and then we set the type here, and then this will be minus base. I've started calling this adder, so I'm going to be consistent. The name is shorter too. Well, I've been consistent some places. Okay, let's see if that still works. So yeah, that still works. That's good. That's good. All right, so we have our read U16, and we have our read U8, read U32. So we're going to want to write U16. Like that. And yeah, I'm starting to wonder if I really should have made U32 the base size. I don't know. I guess it depends on what the types usually end up being that get written to like IO, because that's the reason why you'd want to pick a size at all, really. I don't know. I'll see. We can always revisit this stuff. So if it's BIOS, we do nothing. If it's ROM, we do nothing. But if it's RAM, then we write to the RAM. Of course, that's not quite right. Wait, why does this one shift by? Oh, it's because the ROM is actually, the ROM is written as U16s, I think. Or yeah, it's casting it to a U16. I think that's actually not proper to cast to a different type. I think you're supposed to do a mem copy, but yeah, I'm gonna do a mem copy because that's like the proper way to do this. So I'm going to copy that. This should be value. Yeah, that seems right. Change this over because it's a bit weird. Okay, so same result, which is good. But now we can actually write U16 values. But actually, we've seen writing of all the different sizes, I think. The problem is you can't actually tell writes from reads. Using this syntax, you have to look for, like, basically this is a read, and if the add is on the other side, it's a write. But anyway, I think we've seen them of all sizes, so I'm just going to implement them all. And since, yeah, we'll do it like that. So then, writing. Yeah, so we can't actually do the same trick that I do here, which is like sort of component reading. It's not the right way to do it. So I'm gonna just do this, which is a bit cheesy, but whoops. Definitely will want to do something smarter here, but for now, this seems okay. I think actually one of the rules is that the address has to be aligned. I probably want to check for that. So I'm gonna make it an assert. Should be an assert? I mean, what's really supposed to happen is it's an exception. But what'll happen is if we ever see this, then we can implement it. But until we see it, let's just assume that's an error. Should be, yeah. Okay, so, oh, and actually, that should be the same for these ones. Oh, except, and so then this is the problem, right? Read U16. So what you actually want here is like, this is read U16 and this is read U16 raw. And then this one asserts that the size is oops, aligned, and then this one we just rename. Right, this would be raw. Okay, and that fails because I probably did something stupid. What did I do? Wait, what is this? That's weird. Did I really do something? Okay, hold on. So let's do that. And that works fine. So I had some asserts. Oops. Oh, no, I copied that. Yeah, that's fine. I renamed these ones. What did I do? This is going to be another one of those where people are looking at the video and they're like, come on, find it. Find it, we're all looking at it. Oh, there it is. Yeah, cool. Let's change the... Oh yeah, I've been using that. Okay. So now we want to wire up these right. So we already had them here. So let's see. Maybe this just magically works. Nope. Failed. Interesting. Hold on. That looks right to me. Oops. Oh. Wait, what? Why is this trying to... Why is this trying to write to 4A2? Oh, this is backwards. Okay, well, this is the benefit of checking this stuff out. What this means, I think, is the stage MA right. Yeah, so this is the value and this is the address, and so they're backwards. Is that the only one? That's the address. Okay, that looks fine. That's the address N. That's the address N. Okay, well, we'll see. Whoops. Cool. That looks pretty good. We're still getting FF though. Why are we still getting FF? That must mean that it's not properly mapping the addresses. Right? Probably. So let's try the debugger again. We should be seeing some of them come in here. So let's break 445. Yeah. So that looks right. That's says it's in RAM. That looks right too. Huh. Okay, let's look at the state of RAM. 0. Oh, it's because I didn't add reading from RAM. Come on, gotta use your brain. Okay, so yeah, so this is actually probably this is actually probably wrong, because I think it's actually supposed to be writing big endian, not little endian. Pretty sure. Yeah, big endian. And this assumes little endian. Actually, that's pretty weird. So the ROM is already little endian? Maybe I byte swapped it. I think I byte swapped it already. Which means that you don't have to byte swap it like while you're executing, which is nice. But the RAM isn't going to be like that. So we have to build it up properly, which is fine. But it also means that this mem copy is also wrong. These mem copies are wrong. That's fine. Let's just do it the old-fashioned way. It's simpler anyway. So it's big endian, so this should be that. That should be this. And this is really pretty cheesy, but again, we'll optimize as needed. Oh, and actually, I don't need to mask these because I'm writing U8s, so it'll already mask for me. That works. And it looks like I'm already reading big endian. Yeah, so that's fine. So it just means that here now I want to return state RAM pair header 8, and then this is going to be state RAM that's right. That's a U8. I think it'll get converted to an int automatically. Pretty sure how that's how that works. So let's try that. Cool. Okay, yeah. Now I'm getting real values out of here. So that looks good. That looks pretty good. These are all zeros, but I suppose they could be zeros. But we're still branching here. Let's see. I'm going to commit this, I think. So basically we added writes, LDSL. I'm gonna separate that one out. The rest of these are all about implementing RAM. Actually, this is about adding the address. No, that's not right. That's for what changed here? Oh, changing address to adder. So whatever. And then there's this bug fix here. Okay, cool. And then also fixed. Yep. Cool. So yeah. Looks pretty good. So the next real thing to do would be to, oh wait, what? Oh yeah, so I broke that. That should be working. Why is that not working? Oh, because, Oh, because I, that's why, because I removed it here. Ugh. Oh yeah, look at this, awesome. Oh, this is so cool, yeah, okay, so it got to a new instruction. So, where did it? Where did we leave off from before? I think it was this. I think it was this RTS here, or maybe it was this RTS here. No, this is this RTS from BIOS. And then there's this one. I don't know. All right. Well, I'm pretty happy with what I've got so far. I think I'm gonna probably stop because I actually have to do a meeting tonight for work, which is pretty awesome. So, but I'm pretty happy with the work here. Oh yeah, let's see what we have here. Yeah, so I'm gonna commit this last thing. Let's just amend that so it's back in here. And then what's on stage? Yeah, okay. Let's just make sure that that was looking good. Yeah. Yeah, so I'm pretty happy with how this turned out. Definitely the next things will be like working on the debugger and then maybe implementing some more of these instructions. I don't know. But pretty good stuff. The only thing I want to do, I haven't done it for a lot of the episodes, but the previous ones I was adding this ep to it. So just so I remember where I left off, which is kind of nice. So I think I might do the same thing here and call this ep4. Yeah, that looks good. All right, well, thanks for watching, and I'll try and be a little bit better about recording these, although we'll see. I'll do my best. Anyway, thanks a lot, everyone.